Today we're going to talk about deviations from the ideal gas law. When we're talking about ideal gases, there are some assumptions that we make. One of these is that there are no attractions between gas particles, and the other one is that gas particles are infinitely small and they do not take up space. In other words, the ideal gas law assumes that molecules do not have their own volumes. When we're using the ideal gas law and we're talking about the volume of a gas, what we mean by volume is the volume of the container that the gas is in, and that an infinitely small particle has the entire volume of the container to bounce around in. However, the assumption of no attractions and the assumption that particles are infinitely small, these are not true in real gases. Real gas particles do have mass, and they do have volume, even if the mass and volume are tiny. Real gas particles do interact through intermolecular forces, and depending on the conditions, these intermolecular forces can make a big difference. And these can cause the behavior of the gas to deviate what one would expect based on the ideal gas law alone. So the ideal gas law, PV equals nRT, does not accurately describe the behaviors of gases that are not ideal, especially under conditions of low temperature, small volume, and high pressure. If we try to use the ideal gas law on these gases without modifications, our results could be way off, depending on the gas. Real gases tend to behave like ideal gases when the volume of the container is large, when the pressure is low, and when the temperature is relatively high. In these cases, molecules are moving fast enough that there is very little opportunity for intermolecular force interactions between the molecules. There's also lots of space, so the molecules can't get close enough to each other to affect each other. At high volumes, low pressures, and high temperatures, the molecules don't affect each other, and the size doesn't matter as much. Fortunately, many gases behave like ideal gases at room temperature, and we can often use PV equals nRT as a reasonable estimate. But gases become less and less ideal at low temperatures, high pressure, or low volumes, where the gas particles are getting closer and closer to becoming a liquid. Before we go much further, I want to talk about something called compressibility. This is probably not on the AP exam, but you'll see a lot of graphs that look like this in your textbook and in other places, and you might want an idea of what it means. Now, compressibility is one way that you can assess the extent to which a particular gas behaves like an ideal gas. And you do this by comparing the actual volume of 1 mole of the gas to the molar volume of an ideal gas at the same temperature and pressure. And this is called the compressibility, and it's often represented by the letter Z. And here is an equation for it, where Z equals the molar volume of the real gas at a certain temperature and pressure, divided by the molar volume of an ideal gas at that same temperature and pressure. The main thing you need to know about this is if the gas is ideal, this ratio should be 1. If you were to plot compressibility on the left axis and pressure on the right axis, then you would see a horizontal line for the ideal gas, and we'll look at that in just a moment. But for real gases, sometimes Z is greater than 1, and sometimes it's less than 1. And the take-home point is it's different than what you would see for an ideal gas, and this is a piece of evidence that the real gas is behaving differently. Let's talk about the effect of high pressures and low volumes on real gases. When we're talking about the ideal gas law, volume means the volumes that the particles have to move around in. In ideal gases, the volume of the particles is infinitesimally small, so the volume they have to move around in is the same as the volume of the container. However, in real gases, the size of the particles becomes significant. So if we increase the pressure of a container or decrease the volume, which is often what you have to do to increase the pressure, the particles, which do have mass, are going to take up a significant proportion of the space in the container. So the real volume, which we are defining as the volume that these particles have to move around in, this real volume is less than the volume of the container. It's the volume of the container minus the volume that the particles are taking up. An individual particle doesn't have as much room to bounce around in because some of it's being taken up by its neighbors. Because the particles have less space, they're going to bounce off the walls more frequently and with more vigor. And this tends to make the pressure higher than one would predict based on the ideal gas law. However, depending on the molecule, there may also be intermolecular forces that make the molecules attract each other, and this could result in a lower pressure than predicted, because when molecules attract each other, they might slow each other down, and fewer molecules are going to hit the wall. The take-home point here is that when you get to high pressures and low volumes, between the space that the molecules take up and because of the increase in intermolecular interactions that some molecules have for each other, real gases are generally not going to behave exactly like ideal gases. Under these conditions, real gases also don't behave ideally at very low temperatures. At low temperatures, the intermolecular forces become very, very important. This is because as gas particles slow down, they become more attracted to each other. Some of them may even start to condense. At constant volume, the pressure at low temperatures will be lower than one would have predicted for an ideal gas. The molecules are attracted to each other and they pull on each other. These attractions decrease the force of the collisions between the molecules and the container walls. They may also reduce the number of molecules bumping into the walls, or some of them may even be stuck together in pairs or clusters when they bounce off the walls. Gases with higher intermolecular forces are also more likely to behave non-ideally. Nonpolar molecules, for example, will behave more ideally than polar molecules. So, how do chemists deal with real gases? Well, they use the van der Waals equation. This is not on the AP exam, and you don't need to use it. However, you should probably know that this exists. Van der Waals came up with an equation that corrects for these non-negligible volumes of gas molecules and the intermolecular forces that cause real gases to deviate from the ideal gas law. You'll see that we've added a couple of these correction factors to both the pressure and the volume terms, and the little a's and b's are values that you can look up in a table. My daughter used to refer to this as the funny little equation with the a's and b's that we don't have to use on the test. So let's summarize. Although many gases will behave like ideal gases, at low pressures and high temperatures, the ideal gas law equation becomes much less accurate at high pressures and low volumes and at low temperatures. This is because while ideal gases are defined as having an infinitesimally small mass and no intermolecular attractions, real gases have particles that take up space and tend to have intermolecular attractions.